Chapter 12 is about MIPS processor, right? So in this chapter, in the last class, we discussed just the difference between ACISC processor and RISC processor. And then the next topic was the design principles. That means the characteristics of RISC processor. And another topic was MIPS architecture. Okay, so do you have any problem in any topic of this chapter? Please tell me. In MIPS architecture or in the characteristics of RISC processor, do you have any problem? There are now 32 students and I want to hear from each one of you that do you have any problem in this chapter? Or if I ask questions from any topic, can you give me the answer?
Ma'am, can you repeat MIPS architecture?
Okay, so we can start from the beginning, that RISC design principle. So if I ask you that what type of operation the RISC processor can perform, what will be your answer? In the Viva exam? I can ask you that what kind of operation the RISC processor will perform.
Simple operation, ma'am.
Okay, can you explain it? What is simple operation? What is simple operation? RISC means reduced instruction set processor, right? So for any RISC processor, when the ISA, that is instruction set architecture, will be designed, at that time, very few instructions, very simple instructions will be added, will be included in that architecture. And for executing those instructions, obviously you don't need to write any complex code or compound statements. So all the statements will be very simple statements, very simple instruction, and the RISC processor can easily execute those instructions. So the first characteristic of any RISC processor is simple operation. So what is the meaning of simple operation? For executing any operation, the processor needs two information. One is the opcode and another is the operand, isn't it? So now when the operation is a very simple operation, it can be any arithmetic operation, addition, subtraction, right? So when the data is stored in a register, how the processor is going to fetch the data and how the processor is going to execute the operation. For RISC processor, we know that the operand should be stored in where? In the registers, in the internal register of processor. So yes, when the processor will receive the instruction, at that time, how it will fetch the data and how it will execute the instruction. Or before that, how the programmer is going to provide the instruction. Addition is very simple operation, right? So for addition operation, how the processor is going to execute the task. At first, it will search for the operands, right? And in which location it will search for the operand? In the registers. So it has how many internal register? So many internal register. The RISC processor has large number of internal register. So when it will get the instruction, after that, it will fetch the data from the register and how it's going to identify the register. Suppose the MIPS processor has how many internal register? It has 32 general purpose register. So these are, maximum of these are actually data registers. So the data will be stored here, but how we're going to identify that this register is actually the source, the source data is stored in that register. How you're going to identify the registers? Hello. Do you get my question?
No, ma'am. Can you repeat, ma'am?
Yeah, my question is, suppose this is the instruction of addition operation. Okay, so what is the format of this instruction, the format is, the syntax is opcode and then destination operand, source 1 and source 2. Now, if this instruction is written for an RIC processor, that means these operands are stored where? In the register. And we know that the RIC processor has so many internal registers. Okay, when the processor will decode the instruction from this opcode, it will get to know about the type of operation, and from this part of the instruction, it will get the address of the source operand and the destination operand. That is, from these two registers, it's going to fetch the data, and after executing the operation, it's going to store the data in this register. Okay, so how they're going to identify that among those 32 register of RIC processor or MIPS processor, this one is your first source of this is a register where source 1, the first operand, is stored. This is a register where the result will be stored. How we are going to identify it? For RIC processor. In CISC processor, the register's name will be given, isn't it? That's AX. What is the syntax of CISC processor? Add, destination operand, and the source operand. So in CISC processor, the destination operand, suppose AX register, and the source operand is PX register. So you know that the base register is your source operand. From this register, you're going to collect the data. And after adding these two numbers, you're going to store the result where? In that accumulator register. But what about RIC processor? How you're going to identify your source operand and the destination operands? The register the CISC processor has, suppose the Pentium processor has how many registers? 16 registers, and those registers have some name, they don't have any number. But what about RIC processor? The RIC processor has addresses for each register. Suppose the register is, the processor is MIPS processor, and it has 32 registers. And all the registers have some number. The number or the address of the first register is 0. The address of the second register is 1. The address of the third register is 2. So now, when you write the instruction at that time, you have to give them the address of that destination operand or source operand. Suppose this is your destination operand. So we always use this dollar symbol before the address of any register. So this is your destination operand. That means after adding these two numbers, now the result will be stored in which register? In the first register. That is 0. 0 is the address of first register of MIPS processor, and its name is 0. Okay, 0 register. What about source 1 and source 2? Suppose this is your source operand. So how you'll write your operand? How will write the register? Hello. Hello.
Yes, ma'am.
Is it clear to you? You have to respond. Oh my God, how I'm going to know that is you have problems or not? You have to speak up. Is this topic clear to you, that how you are going to write your destination operand and how you're going to write the address of your destination operand and source operand? Is it clear or not? I don't know why I don't respond. Is it clear to you that how you'll write the instruction? How we're going to identify that the source data is stored in that register, the destination operand will be stored in that register. How we're going to identify it? Hello?
Yes, ma'am.
Is it clear or not? Can you please tell me, is it clear or not? If you have problem, then I'll discuss that topic again. Look, the operation is addition operation, and for RISC processor, we know that the syntax is opcode, the destination operand, the first source operand and the second source operand, right? What about CISC processor? The syntax is opcode, destination operand, and the source operand. Okay, so suppose you want to add these two data 5 and 2. So where you will store these two data 5 and 2? Where you will store the data 5 and 2?
I mean register.
Register. Source 1 and source 2.
ISC, then the data can be stored in register or in memory, right? Or you can use this constant also. Your addressing mode can be immediate. CISC processor supports 3 or 4 types of addressing mode. So your data can be stored via in some registers, in some memory locations, or you can use this constant value in your instruction also. It's possible. So suppose we're going to store the data into register, right? So now when the processor, the Pentium processor, which is a CISC processor, will receive the instruction. So at first, if the instruction is add AX, BX. So when it will receive this instruction now, it's going to decode it, right? So when it will decode the instruction, this is the field where the operands locations are given, and this is the field where the type of operation is given. Okay, so now the opcode is that. So the processor is going to perform addition operation. And what about the operands? Now, this is one source operand and this is another source operand, but this operand will be used as the destination operand also, right? Now look, the registers names are given that AX, BX, and how many data registered the Pentium processor has total? 4 registered AX, BX, CX, DX. So if the registers names are not mentioned here, then how the processor is going to locate the operands? Suppose the names are not given. So at that time it needs to check all the data register of Pentium processor. But now in this instruction, the registers names are mentioned that AX is your destination operand as well as one source operand, and BX is another source operand. So now suppose 2 is stored inside the BX register and 5 is stored where? In the AX register. So now the processor will collect the data from which registers? From AX and BX. So after getting the data, now it will execute the operation plus. So 5 plus 2 equals to 7. So where, in which register the data will be stored? In CX register, DX register, in which one?
Ma'am, AX.
AX, ma'am.
That means the name of the registers are given. That's why the processor knows that it is this register is its source register, this is its destination register. Now it will change that register value. Now the new value of accumulator register is 7. So this is for which processor? For CISC processor. So in CISC processor, the processor can easily identify the source operand and the destination operand from where? From the instruction. If these are memory location, then the name of or the address of the memory locations will be given. If these are registered, then the register's names will be mentioned. What about RISC processor? So now suppose the RISC processor is MIPS processor. MIPS R2000 processor. So this RISC processor is 3 address processor. So there are 3 addresses: destination address, source 1 address, source 2 address. So now the operation is addition, but now the processor is going to perform how many? The processor is going to add how many numbers? 2 numbers, right? And the numbers are 5 and 2. So in RISC processor or in MIPS R2000 processor, we know that there are 32 registers. And these registers also have some names, but when you will write the instruction for our RISC processor, at that time, we will not write the name of those registers. If you want, you can write the name, but usually we write the address of the register. So the MIPS processor has 32 registers and the address of the registers are 0, 1, 2, 3, 4. These are the address of the register. For the last register, address is 31. So these two data, 5 and 2, can be stored in this register or in register 5, right? So how the processor is going to know the location of the source operand and the destination operand? We have to mention the address of those registers, isn't it? Suppose the source operand is 1, another source operand is 2. So how we are writing the address? The address, the source operand should be started with the dollar symbol and then just write the address of the register. So the source operand is 1 and another source operand is 2. So in these two registers, the source operands 5 and 2 are stored. So after adding these two data, now suppose the destination operand is 0.
H0, ma'am.
Okay, so now in this register, the result will be stored. So these are the difference between these two instructions of CISC processor and RISC processor. In CISC processor, the addresses of the registers will be given. These are, sorry, the names of the registers will be given, right? AX, that accumulator register, BX, base register. But in RISC processor's instruction, the address of the register will be given. Clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now, another characteristic is this RISC processor is fixed length. RISC processor has fixed length instruction. But the CISC processor has variable length instruction. Why? All the instructions of RISC processor are same length, but in CISC processor, the lengths are different. Why?
Ma'am, in RISC, we store every data in individual register. And the CIC, we don't, ma'am.
So where
And the
is
register size are always fixed, ma'am.
yeah, the registers size are always fixed, okay? But what is the proper explanation? Why CIC processor's instructions are variable length instruction, but why the RISC processor instructions are fixed length instructions? I discussed this topic in the last class. Tanvir Ahmed. Tanvir Ahmed. Tanvir. Sabrin Islam. Hello, Sabrin. Hello. Okay, can you please raise your hand that how many of you actually know why RISC processor instructions are fixed length instruction? Please raise your hand. Tassin, okay. Sadia Frin. And then okay, so Sadia, can you tell us why RISC has fixed length instruction?
Yes, ma'am. RISC has fixed length instruction because we used here only register. But
Okay.
But in CISC, we used register as well as we can use this addressing mode as immediate addressing mode, then direct addressing mode and indirect addressing mode. That time our operands bit will not all the same in all time.
Okay.
That's why CISC is not fixed length, but RISC is always fixed length.
Yes. So the main reason is the addressing mode. In CISC processor's instruction, the operands can be stored where? In registers, in computer memory, or it can be any constant. But what about RISC processor? In RISC processor, there is only one addressing mode. See, all the operations are actually register to register. Suppose this instruction is for addition operation, and the destination operand source 1 and source 2 operand, all these operands are actually registered. What about CISC processor's instruction? The opcode is add, and then destination operand, source operand. Now the CISC processor has 4 addressing mode. These are direct memory addressing mode, indirect memory addressing mode, immediate addressing mode, and register addressing mode. So your destination address and source address can be registered. Your destination or source in the address can be memory address. It can be immediate address. What is immediate address? That means here as source operand, we can take any constant number. So now when your assembler for CISC processor, we can use NASM assembler, that is net-wide assembler, or MASM assembler, that Microsoft assembler. Okay, and for RISC processor, for MIPS processor, we can use SPIM simulator. This is an assembler. So what is the function? What is the responsibility of the assembler? Their main responsibility is they will translate each assembly language instruction into machine language instruction. What is machine language instruction? In machine language instruction, for each field of the assembly language instruction, we'll get a binary number. Suppose add is the opcode. So when the NASM assembler will translate this opcode into binary number, maybe you'll get a 6-bit or 8-bit, it depends on the type of the assembler. So 6-bit opcode. Okay, so that means for a particular assembler, the number of bits for any opcode is fixed. For any opcode, it can be add, sub, multiplication, division. Always we'll get a 6-bit binary number when wire in machine language instruction. Now, what about the destination operand? The destination operand can be registered, it can be any memory address, it can be any immediate, sorry, it cannot be actually immediate address. So now, when the destination operand is a register, at that time, how many bits will be used for representing that register? 5 bits. When the register name will be translated into binary number, it will be a 5-bit number. Now your source operand, if it's a memory address, then if the processor is a Pentium 32-bit processor, then the number, that source address will be a 32-bit address. Right. Now, if we add all these binary values, at 6 plus 5 plus 30, what will be the length of instruction? The length will be 45. So total 45 bits are needed for this addition instruction, isn't it? This instruction can be represented in binary language by using how many bits? 45 bits. Okay, now your destination operand can be a memory address. At that time, what will be the length of instruction? If both the destination operand and source operands are memory address, then total number of bits will be 70. Right? Now you can see that for different addressing mode, the length of the instruction will be different in which processor, in CISC processor. But what about RISC processor? In RISC processor, the destination address, the source address, and the second source address, all these addresses are the address of register. Okay, so now for a RISC processor, suppose 6 bits are needed for encoding, for translating the opcode, for converting the assembly language instruction into opcode into binary language opcode. Okay, so 6 bits for the opcode, and for each of these register, now each of the register will be translated into 5-bit binary number. So total, how many bits are needed? 5 plus 5 plus 5, 15, 15 plus 6 equals to 21. So for a particular RISC processor, if it uses this number of bits for encoding, for translating the register's address, and for translating the opcode, then for any operation, for any instruction, the length will be 21, because in RISC processor, there is only one addressing mode, and this is register addressing mode. That's why the RISC has fixed length instruction, because for any operation, when you write instruction, it will be translated into similar length binary language instruction. But what about the CISC processor? In CISC processor, we can use several types of addressing mode. So if particular addressing mode, you will get a particular number of bits in any instruction. So since we have different types of addressing mode in CISC processor, we can have different or variable length instructions for which processor? For CISC processor. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Please raise your hand. If this concept is clear to you, then please raise your hand. Only 1, 2. So Tibanita Roy, Mahfuzur Rahman, Mehboob Hossain, Sabrin, then Gulshan Ara. So this concept is not clear to you, right? Hello, Sabrin Islam. I think they're not even listening to me. Okay. So now the next topic is the MIPS architecture. MIPS R2000 architecture. So this is a Pentium this is RISC processor. So what is the architecture of MIPS R2000 processor? So the architecture means that you just have to define how many units that processor has, how many internal register that processor has, how many circuit it has, or how many flag register it has. Okay. So we know that the biggest responsibility or the main responsibility of the processor is to execute the task. And when it will execute any instruction, or it will execute any task, when it will get the instruction, right? And the instruction has two fields. One is operand field, another is opcode. So actually the processor needs to know what type of operation it's going to execute and on which data it's going to perform that operation. So the processor needs to receive two information. One is the operand and another is the type of operation, that is the opcode. Now the processor will not directly receive the data from the instruction. In the instruction, only the location of the data will be given. Only the address of the data will be given. Okay, so there will be two units. One is bus interface unit, another is execution unit. So the execution unit helps the processor to execute all the arithmetic and logical operation. And from the bus interface unit, the processor will receive the location of the operand as well as the instruction. Now this MIPS processor has also two units, bus interface unit and execution unit. It has ALU circuit where it will execute the task. It has temporary register for temporarily holding the data. But the thing is how many internal register it has and what are the responsibility of those internal registers. So the MIPS processor has 32 internal or general purpose register. R2000 provides 32 general purpose registers, a program counter, and 2 special purpose registers. All registers are 32 bits wide. So the MIPS million instructions per second R2000 processor has total 35 32-bit register. There are total 35 registers and all these registers are 32-bit register. Okay, there are 32 general purpose registers, a program counter, and 2 special purpose register. So this 32 general purpose register has some specific functionality. Look at this figure. These are the register. Okay, 0, 1, 2, 3, 4, 5. These are the address of the register. And this 0, AT, V0, V1, A0, A1. These are the name of the register. So the MIPS processor has 32 general purpose register and their addresses are 0, 1, 2, 3, 4, 5 to 31 and the name of these registers are 0, AT, V0, V1. Okay, so there are total 32 general purpose registers. And what is the function of this register? The first register is 0, its number or address is 0 and it's used for initializing the register as 0. Okay, and what about the AT register? Its number or address is 1. The register is reserved for the assembler. And what about the third and fourth register? The number of the third and fourth register is 2 and 3 and their names are V0, V4. So when the main procedure will call another procedure, at that time the result of any procedure will be stored here. Okay, then register 4 to 7, arguments 1 to 4. So if your program has 2 or 3 procedure, at that time the main procedure needs to send the parameters or the arguments to another procedure. So at that time these registers A0, A1, A2, A3 will be used for storing the parameter. Okay, so these 32 registers has some specific functionality. What about the special purpose register? There are 2 special purpose registers, one is HI and another is LO. And these 2 registers are called multiply and divide register. That means after any multiplication or division operation, the result will be stored where? In these 2 special purpose register. And these 2 registers are 32-bit register. 0 is the LSB and 31 is the MSB. Okay. So how this register will store the result of multiplication and division operation? There are 2 special purpose registers, HI and LO. And these 2 registers are 32-bit registers. So total 32-bit data can be stored here. So what is the result of multiplication operation? What is the result of a multiplication operation? In multiplication operation, if we multiply to n-bit number, the result will be a 2n-bit number. So this is our result. These are our source operands and this is the result. Okay. Now suppose this multiplication instruction is written for RIC processor. So in RIC processor, where you will store these 2 operands? Or what will be the length of your source operand? In RIC processor, you have only one addressing mode, that is register addressing mode. That means all the data, all the source operand or destination operand will be stored where? In the register. And this RIC processor or MIPS processor has 32-bit registers. So all the registers are 32-bit registers. So when you will take any source operand, suppose the number is 15, the number is 20, 30, or it can be 500, 700, but the number should be represented as 32-bit number because your register is 32-bit register. So when you multiply to 32-bit number, these are your 2 source operand. Okay, so the result will be a 64-bit number because 2 into 32 equals to 64. So in which register you will store it? Because do you have any register which length is 64? Do you have any register in MIPS processor?
No, ma'am.
All the registers are 32-bit register. Now we are going to use two special purpose register HI and LO. So this 64-bit number will be divided into, suppose this is your result and it's a 64-bit number. These are the bit position, suppose this LSB 0, 1, 2, 3, 4, then 62, 63, 64. Okay. So now this is your low, this is a lower half of the result, all the bits from 0 to 31. So this is your low order 32 bits of the result, right? And all the bits from 32 to, it's actually 63. All the bits from 32 to 63, these 32 bits are high order 32 bits of the result. Now this low order 32 bits will be stored in the special purpose register LO, and the high order 32 bits will be stored where in HI register. Is that clear?
Yes, ma'am.
For any, just remember that for any operation, we need some operands, as well as we, after executing that operation, we will get a result. Okay, so now look at the length of the operand. Your source operands are 32-bit numbers, so you can easily use any register of MIPS processor, but the result you got is 64-bit number. But in MIPS processor, there is no such register where the length is 64, the size is 64. So now you can do one thing, just use these two special purpose register, because these are called multiply and divide register. So now, and these registers are also 32-bit register. So the low order 32 bits will be stored in LO register, and this is for high order bits. So this is a multiplication operation. What about division operation? In division operation, there are two source operand, that is divisor and dividend. And there are two result. One is quotient and another is remainder. Okay. So now the divisor and dividend are, the dividend is a 32-bit number and the divisor will be also 32-bit number. But if you want, you can use 64-bit number also. Right. So now, if your divisor is 64-bit number, then you need how many 32-bit register? Two 32-bit register, right? So your dividend, the minimal size of your dividend will be, sorry, this is the size of divisor and the dividend will be 64-bit.
Yes.
Okay. So now when the divisor is 32-bit number, the quotient and remainder will be also 32-bit number, right? So after dividing a 64-bit number by a 32-bit number, now you got a 32-bit quotient and 32-bit remainder. So this special purpose register HO and LO will be used now. So which one will be stored in HI register and which one will be stored in LO register? The quotient, the result will be stored in LO register. This is for the quotient and HI for the remainder. Clear?
Yes, ma'am. I have a question. Ma'am, if we use a divisor 64-bit, then dividend 128-bit, ma'am. On the time, how can we do it?
No. If your divisor cannot be 64-bit number, at that time you need two 32-bit register. That's why I said this is the maximum. Sorry, for any RISC processor, suppose this is the minimal or the maximum limit of your divisor.
Okay, ma'am.
Here. It has another 32-bit register, that is program counter. So what is program counter? What is the responsibility of program counter register? This is also 32-bit register. 0, the last bit is 31. This is RISC processor. What is the name of the processor? MIPS, right?
Yes, ma'am. Yes, ma'am.
So in MIPS processor, the length of the instruction is fixed and the length of the instruction is 32-bit. We are going to discuss it in the next chapter, chapter 13. For any MIPS processor, the length of the instruction is 32 bits, and this program counter is used for placing all the instruction bits. Suppose the processor is going to perform addition operation. So when you write that assembly language instruction, at first, the SPIM simulator, this is the assembler of MIPS processor. This SPIM simulator will translate that assembly language instruction into 32-bit binary language instruction. So all these 32 bits will be stored here in this program counter register. So the instruction bits will be stored where? In this program counter register. Is that clear? This is just like the instruction pointer register of CISC processor. In that processor instruction pointer, all the instruction bits are stored, right? In program counter also, the instruction bits will be stored, that what kind of operation the processor is going to execute, as well as on which data the operation will be performed. So program counter is used for providing the instruction to the processor. Is it clear?
Yes, ma'am.
So in the evening, we have a class, so please don't miss it.
Ma'am, I missed my attendance.
Okay,
Ma'am, I also missed my attendance,
Yeah.
23.
so today from 5:25, we have a class. Okay. So the first serial number 1 to 23, please join the session at 5:25 p.m. And serial number 24 to 46, please join at 7 p.m. Okay?
Okay, ma'am.
Okay, so serial number 45 and
Yes, ma'am.
Ma'am, 23.
23.
Ma'am, 17.
17. Okay, then thank you.